Hello, everyone. Let's talk about neural network a little bit more. We're going beyond the vanilla recurrent neural network architecture. So these are a couple of study material. I just hope that you will read and follow the lecture. All right. So the issue with the vanilla recurrent neural network is the vanishing gradient problem. Uh, so the problem is actually that unless that you take a extreme measure or a specific measure, your gradient will become zero, and you'll see that in gradient update, and the weight update, you can't really see that there is any change. So meaning actually your model will experience hard time to convert. So the solution is use clever tricks like weight initialization, equal state network. This is a special type of architecture uh, you can read about, but I'll probably not cover this in this course. Long short-term memory and gated recurrent neural network architecture. So the topic of this particular lecture is LSTM. Let's focus on that. So the concept of recurrent neural network is this, and the long short-term memory architecture. So the basic vanilla architecture is you don't throw everything away. Start thinking about from scratch again. Your thoughts have persistence. So imagine you want to classify what kind of event is happening at every point in a movie. It's unclear how a traditional neural network could use its reasoning about previous events in the film to inform later ones, right? So that's very important that you understand is that it's a chronological event, right? And not everything that we should memorize to decipher what's going to happen next or what is what has happened, what has been happened, right? So that's very important to realize that. And I believe, please take a look at these applications of sequential learning. This has come and is a product of AI uh, to write movie scripts. Right? So this is and also music and poem and all these different cool things, and you can understand, start to think about since the last lecture. You can start thinking about how to use uh, the idea of recurrent neural network to do all these different cool stuffs. These are language modeling, and language can be anything. So the concepts here actually, let's first focus on some of the notations. So A is the A is some neural network that takes xt as input at time t, and ht is the output. There you can see a loop. Uh, this is the information to be passed on one time step. Right? So this is this is the same recurrent neural network that we talked about, and this is the cell, right? So everything happens in here, right? So this is the hidden layer, right? So this particular hidden layer, and also we unrolled this, right? So we realized that if we pass the first word, you can get the next word as a prediction result, and so on and so forth. So nothing has changed, but so let's talk about uh, going beyond the vanilla architectures of recurrent neural network, which is the long short-term memory, is the problem of long-term dependency. So one of the good thing about recurrent neural network, the vanilla architecture of recurrent neural network is that they might be able to connect previous information, distant information to use what's going to happen, what is going to be the next word or next event, and so on and so forth. Sometimes we only need to look at recent information. The present task depends on maybe a couple of words. Just an example, say I was up all night wondering where the sun had gone. Then it dawned on me, sky is dash, right? So the word that you expect the model to predict, uh, it can be, I mean, so how long do you want the model to look to get the context in here? So that's the language dependency, long-term dependency. And also this is just a joke, I guess. Answer to the life, the universe, and everything. Google it. The answer is 42. Just a joke. Anyway, and also you can see actually that this is a paragraph about something. I mean, someone's personal experience, and then you you expect, or what do you expect the model to predict? So that's a couple of things that, I mean, probably this is Steven Spielberg's story, right? So based on how long ago, I mean, we want the sentence completion module to use. So that's a couple of things. I mean, just have that in your mind. Actually, we're dealing with what information is useful to do a task. And the task being, say, maybe we would like to classify or we'd like to predict what's going to be the most probable next word. Okay. So most probable next word might not be, I mean, dependent on, I mean, very far away word. I mean, meaning actually that from the beginning of time, the words has, I mean, the spoken words or from the vocabulary might not affect much in the later uh, predictions. All right, so in such case, where the gap between the relevant information and the place that is needed is small, right? RNNs can learn to use the past information. So, so we need to understand actually how long the memory will be to predict the next word, right? So language modeling with memory in it. So as the gap grows, so here actually that in the previous slide, maybe so this one is dependent on multiple one, and you can imagine actually that uh, everything, since everything is a chain of the gradient calculation is definitely a chain of functions, right? So it's definitely dependent on the x naught, right? All the way to the first token. But as the gap grows, I mean, as you see that the recurrent neural network becomes unable to connect the information present in the very past, right? So that's a couple of things, and also that will create the vanishing gradient problem. The LSTM, the long short-term memory architecture, solves it with a clever trick. So, so recurrent neural networks are called recurrent because they perform the same task for every element as of a sequence without being dependent on the previous computations. So this is the basic architecture of recurrent neural network that we have known. So these are recurrent neural network. I don't know whether I'm missing the slides. Where is it? Give me just a second. All right, so let's All right, so this is the long short-term memory architecture, where you see that it is very similar uh, to the vanilla architectures of recurrent neural network, except the hidden state is now become this, right? So within the cell, we no longer do the simple that ux plus ws and pass it through the hyperbolic tangent. And then, so we no longer do that. So it's a little complex than the vanilla design. Right? So an xt goes in, and what happens here is there you'll find two cell lines, right? So one is uh, the hidden, uh, in, I mean, the H line, and C is called the memory line. Right? So where, I mean, you'll see that, so a couple of activation functions. So the new information, so for example, XT is the new token, right? It goes in, and with the help of a sigmoid activation function, you can tune the volume up or down to contribute into the memory line. I'm not sure whether it is making any sense to you, is that you can amplify the importance of a certain token or de-amplify the contributions of the token based on the loss function. But anyway, so we'll go there later. So this activation function helps in modifying that value, right? And the memory cell uh, learns about that in here. And also at the same time, we are including, I mean, so this plus sign that you see here, meaning actually whether to retain it or forget it, right? Not everything should be stored in the memory line. Uh, so we'll definitely, so we'll add something that is relevant, and everything else we'll forget. So that's why it's called the short-term memory. But again, we'd like to emphasize on long short-term memories. Right? So with limits. All right, so uh, let's keep that particular example. Notations. This is a neural network layer. A pointer is warp operation, vector transfer, meaning that actually vector quantity is going from one unit to the next. If you see a fork like this, I'm sorry, this is the merging. If you see that the two matrices or two vectors are going to be concatenated, and if you see this, the same thing is going to be copied into multiple units. All right, so this is the output of from the last unit, right? So again, this is the same recurrent neural network, except in this particular unit, we do all these different operations. You see that actually we're changing that cell, uh, S cell, which from the vanilla layer that you saw that. All right, so the current input, this is the output from the last layer, which is H from T minus 1, right? T minus 1 times that, and that is the memory line, which is C. And here, wait a second. So H is the output that is going, I mean, that is calculated based on all these. So given the current input, this is the output HT. So in the memory line, you see that's a new updated memory. So after every, I mean, this kind of an unrolled version that you see. So after this processing, your memory line will be updated. Right? So you will have CT, and also your new output line is going to be HT. So the scaling of the data, whenever you see a cross there, I mean, the scaling of the data, amplifying, de-amplifying, based on whether this input token is relevant to the output prediction. So how you're going to decide? Let the back propagation take care of that, because you are, this is a supervised learning algorithm. So uh, at some point, actually, you are going to be calculating loss or the error, and you will decide actually what's going to be the value for that. All right. So adding new information is this. I mean, if it is important, it will be added. Otherwise, it will be forgotten. So why hyperbolic tangent? Many a times, actually, you see in the LSTM cell, so there is a hyperbolic tangent twice. Uh, so since its span is bigger than sigmoid, it looks like the shape of the hyperbolic tangent is similar to sigmoid, to that of the sigmoid, but uh, tan is used to span a little bit more, so negative minus -1 to +1. Uh, we can reverse that. Sigmoid specifically is used as the gating function for the three gates: input gate, output gate, and forget gate in LSTM. Since the output values are between 0 to 1, so amplifying or de-amplifying is helpful on that. Uh, so just these are a couple of examples that you can look over. Okay, so let's break down the LSTM cell. Uh, the first is the memory line. Okay, so the key to LSTM is the cell state. See the horizontal line running through the top of the diagram. The cell state is kind of like a conveyor belt. Okay, it runs straight down the entire chain with only some minor linear interactions. And these are bad interactions. Whenever something gets multiplied or being added to the to add new informations to the memory line. So LSTM has three types of gate: input gate, output gate, and the forget gate. Let's dive into those. Gates are a way to optionally let information through. They are composed of a sigmoid neural network layer and a pointwise multiplication operation. Okay, so the sigmoid layer numbers between 0 to 1. The sigmoid layer output numbers between 0 to 1, describing how much of each component should be let through. The value 0 means let nothing through, value 1 means let everything through. So this brings the forget gate layer. All right, so this guy, this is the forget gate layer. So FT. So the output FT is essentially this, right? So you have W times. So you see that this is a concatenation of these two quantities, XT and the HT, which I mean you'll find resemblance to the vanilla recurrent neural networks. I mean functions, right? And don't forget about the pipes. So this is the forget gate layer, and in such problem, the cell state might include the gender of okay, this is based on the example. I'm skipping that. The first step in our LSTM is to decide what information we are going to throw away from the cell or the memory cell. So this decision is made by by a sigmoid layer called the forget gate layer that you saw. Very slow here. So this one, right? So the input. Uh, right. So it looks at the previous output and the current input. And it outputs a number between 0 to 1 for each number in the cell state. So 1 represents completely keeping it, 0 represents completely getting rid of it. All right, so then input get layer is calculated based on this formula. It also has a sigmoid in it and a hyperbolic tangent. So if you ask this, so we would like to, so that's the, I mean, how that input becomes part of the cell. So what information, what new information we're going to store is determined by the input get layer. So that's a couple of things. The first is the sigmoid layer called the input get layer. It says which values we will update. And hyperbolic tangent layer creates a vector of new candidate values for CT. That should be added. So in the output get layer, so the next one is the output layer. You just do the arithmetic here is so this one is multiple. I mean, the fine tuning the XT information that forget get layers, whether to throw out or throw away or keep or in the middle or any value. You can see that this there is a potentially a span between 0 to 1 to in the forget get. So this one plus so this one is multiplied with the original CT minus 1, and the new information is updated, which is plus the input IT times the current CT. So that's the output get layer. So it is now time to update the old cell state into CT. C at time step T. So and finally you calculate the output, right? So OT is this, and you just multiply that, which T is calculated based on that. So we run sigmoid layer, which decides what part of the cell state we're going to output. Then we put the cell state through the hyperbolic tangent and multiply it by the output of the sigmoid layer, so that we only output the parts that we decide. All right, so so these are a couple of components of the LSTM. So the first component is the forget get. Sigmoid layer takes the input and decides what part from the old output should be removed. All right, so the output of this get becomes FT and CT minus 1. Second component is the input get. And the third component will decide what is going to be the output, the final calculation. All right, so I mean, as in a summary, so these are the functions calculated within the LSTM cell. Right? So the input, the forget, the output, and then you calculate G, CT, and ST. And so an LSTM layer is just another way to compute a hidden state. Right? So previously in vanilla recurrent neural network, ST was calculated based on this function. But so now you see that the ST is calculated here, which is the cell line, which is the memory line, element-wise multiplication with the output. Right? So you see that it didn't. I mean, it is calculated based on this particular function. So there is some difference there as well. Okay, so the LSTM unit does the exact same thing, just in a different way. This is key to understanding the big picture. So you can essentially treat LSTM units as black box, right? So within the box of these functionalities are can't happen. All right, so LSTM and also gated recurrent unit is a simplified LSTM. I'll throw some slides at you. I mean, some tutorial at you on GLE. So these are the three gates in the LSTM unit: the input gate, forget gate, and output gate. These are calculated based on this with, right? So once we, and also the candidate hidden state G is based on this formula, and then this is your internal memory architecture is going to be CT, which is so you remember that actually CT minus 1 is the memory line before before T. So based on this, I mean, you calculate the forget function, and then you add the new information that is coming from the input gateway. All right. So, and finally, this is the output state. Right. So given the memory CT, I will finally compute the output layer by multiplying the memory with the output gate. Not all the internal memory may be relevant to the hidden state used by other units in the network. All right, so this is actually these kind of gating by forget gate, input gate, and output gate. You can see actually find some resemblance to physics gates. I mean, this is electronic circuit gating mechanism. Whether the input comes in and it may pass or not pass the information to update the current memory, which is C. And there is also a gate, which is the output gate. So the output gate determine what's going to be the output, right? So you have to close it to let the electricity pass, something like that. So whichever mechanism helps to understand that, right? So this is the overall architectures of the LSTM cell, LSTM architecture, and this is this particular inside box, which is very different than the vanilla recurrent neural network is replaced by this, having three types of bits. All right, so this is also another architecture of LSTM cell. And the reason actually why I put this here, because the notations and nomenclature might be easier to track or find in the source code that I'm about to show you. All right, so CT minus 1 is the C is the memory line. D, whenever you see a D is the gradient. All right, so once you know this, let's code. This is similar language modeling with LSTM. Read and pre-process data. So right now, actually, we are reading from Shakespeare. Shakespeare's most works, if it is placed in a text file, you'll find this in the I mean alongside the Jupyter notebook. So you just read it, and this is the data, right? So we'll teach the neural network, the recurrent neural network, to generate text like Shakespeare did. And also the good another thing is we're not, I mean, tokenizing that. I mean, in a way that actually this is not a word level generator or word level language model. The way that we're going to be building this is a character level language model. All right, so meaning actually that if you pass T, what's going to be the next character, and if H is the next character, what is going to be the third character, and so on and so forth. So that's it's the character level language model. All right, so you will see that the data has almost 100,000 characters, 62 are unique characters. I mean, 62 unique characters. The data size is almost 100,000. Uh, and again, you may want to use the indices, right? So character to index and index to character. Since there is only 62 characters, so you don't want to, what's it, restrict your vocabulary size here, which is 62. So everything is here. We can afford that. So the hidden step size, I mean, hidden layer size is 100, time steps 25. These are a couple of hyperparameters. Size of concatenate H and X vector uh, is that. So the number of hidden layers versus time steps, we can see that we can unroll this. But again, so you see that there's only a single neuron. I mean, you see that there is a single neuron, but we can have multiple neurons, like say hidden layer having 100 neurons. So definitely the figure is going to be look like this. So don't get strange by this. All right, so the sigmoid function and its derivative, hyperbolic tangent functions and its derivative. And we'll do LSTM from scratch. So we need to learn different gradients calculations. So these are defined here. Remember again, that is just another revisiting the notations of LSTM cell. So these are these are the several classes to define that the parameters of the LSTM, which is, I mean, what is it? So imagine that there is WF, WI, and WC, and WO. These are a couple of weights associated. And in the forward pass, you see that this happens, right? So, and you predict the output. So C is the concatenation of H and X. I don't know why that function is there, but just a second. So sigmoid, this is probably demonstrating how sigmoid or softmax work. Sigmoid function is an element-wise function, so it changes that. This is the loss function, and these are the gradients of all the weights that you saw in the LSTM. So now the notation may matter. So everything is, you'll find this as a reference, and then apply that into calculating the gradient and do back propagation. So you calculate all these gradients. And there's a couple of housekeeping with gradients, just to see actually if one of the gradient, this is actually the contrary or opposite of a vanishing gradient problem. If it explodes, definitely you may need to use gradient clipping to clip at certain and HT and CT at the final loss. So is actually more towards the implementations and updating them, updating all the weights. So once this is done, so what we're going to do is we need to predict the next data, the way that we did for word level, granular neural network is generate the next character. Right. So first to the training, right? So we are so this is actually uh, thoughts the training process. Yeah. And also we update the weights based on the gradients that we collect. And this is what we do here. And I've registered a keyboard interrupt because actually uh, it doesn't it doesn't stop. Uh, so it's given the first character, it predicts the next one and the next one and next one. You may want to stop at some point. So a keyboard interrupt is registered to stop the infinite loop. Right? This is loss calculation. So the training loop with the keyboard interrupt handler registered, you just put that into the loop and then see actually what happens. So this is actually the loss function, the loss values, and it decays over time. And at the same time, you can see that so we are printing a bunch of, I mean, characters. Say, for example, maybe there are about 100 characters based on this. So that you can debug and see actually whether the model is learning a good sequence. All right, so gradient check is also used to validate or see actually whether it is suffering from vanishing gradient or excluding gradient problem. We saw this type of function before. So we just so these are the checks, and once the check is done, you can try out actually the LSTM model that was just used, and to see actually whether it is generating valid words or valid sentences. All right, so that's one part, and we can apply LSTM or granular neural network to do prediction for stock price. So the training range that you see here is between it's a 5-year window. This range is right after the 5-year ends, which is the first month of every month, I mean every day in the following month after the training stops. And we want to predict the open stock price. Let's load the data. And it's also you'll get the data with the Jupyter notebook as well. So the training data set and the test data set, and plot it here. So this is the open values on the test data set that we'd like to predict. And since this is a time series data, we want to know, we'd like to model that whenever there is a spike or a flatness, whether the trend is captured by the model. All right, so we, uh, we converted this into a 60 time steps window, right? So that you can consider this as the vocabulary. So all right, so it's train, white train, Uh, is a couple of rudimentary design, and also now this is I mean, since all these computational frameworks also support LSTM, recurrent neural network modeling. So it has LSTM. Let's use that. Just has sequential, the way that you can construct it, convolution neural network, you can pretty much do that. How many units and return sequences, because we will add more layers later on. And also use dropout as a regularization. We talked about that before. All right, so you see that actually we're adding a bunch of layers. So the first layer, this is the first LSTM layer, then we add another one. So true, we'll add more layer. This is the third LSTM layer. This is the fourth LSTM layer, and we tell that's it. So this is actually how we construct multiple LSTM layers. And finally, actually, you'd like to predict the open value, the target value. So you'd like to add that as well. Then we compile the way that we compiled before, and then we run fit function. Take a look at the loss value to get an idea. So this is the test data uh, based on the this, this is the test data set, the ground truth open values, open stock prices. So let's see actually where is the predictions, right? So uh, let's predict that with the model that we have just framed. It's test. All right, so this is scroll down. So, and you can see this. This is the plot that you saw, and it's you see there's a subtle difference. The blue line is the prediction, the red line is the ground true value, and by looking at the blue line, you see that this is not exactly following the exact absolute values of the open values or open stock prices, the ground truth, but it follows the trend. So that's one of the inferences up until this point is we can definitely always fix this, how's it, the scale or by a base value for the stock. We can fine tune that later on, but take a look at this seasonality of this, or the pattern or the trend of the stock price. Uh, so the model with only a few epochs, it learns those patterns. So that's the good thing. And also this time is in future, meaning that actually your training data training data is based on 5 year, which ends in December 31st, 2021 or 2016. And in the following month, every single day, we predict. Right? So that's one of the things. All right, so I guess you get the idea, and I hope that you'll play with these tools and I mean the Jupyter notebooks that I've given you maybe uh, to, uh, to try out first is to produce the results and try out different many other things like modeling music uh, and modeling stock prices might be more profitable as well. Anyway, so I'll stop here. I'll see you next week. Thank you. Bye.